control input of U. So we minimize the cost function subject to a set of constraints. And the constraints are equality constraints. So assume we have M constraints. So we also define the number of control inputs is greater than the equality constraints. So to solve the problem, the formulation is quite standard. We try to convert the constraint optimization problem into an unconstrained optimization problem by augment the cost function using the Lagrange multiplier. So we define the solution is like this. We define a Hamiltonian. So the Hamiltonian is the augment cost function. So the original cost function plus a linear combination of the equality constraints. So if we augment the cost function in this way, we know the J itself is a scalar. So this product is also a scalar. So the H will be a scalar. So for a scalar, you know how to calculate the derivative, how to decide the gradient. So once we construct this Hamiltonian, the solution is very standard. We just calculate this pH. So I also want to highlight that if we augment the cost function in this way, we actually convert the original constraint optimization problem into an unconstrained optimization problem. So it's become a standard unconstrained problem in terms of U and lambda, two sets of control inputs. So based on the necessary condition that we derived in the first part, we know the condition to achieve the minimizing point is the gradient to be 0. So the gradient, there should be two sets of gradients. So the first set of gradient is the dH, du. So this must be equal to 0. And secondly, the dH, d lambda. This must be equal to 0. So these two equations will give us a set of algebra equations so that we can derive. So from this, you can derive the U star. So these are the problem and solutions for the constraint problem with equality constraints. So in the last lecture, I also gave you homework for you to try it. So we want to minimize function of in this form. So probably you already tried. So the solution is the U1 star is 1 divided by 10, and the U2 star is 9 divided by 20. So these are the solutions. So to solve the problem, it's quite straightforward. So we construct the H So the h is given by this j plus, so we already know the j is just a scalar function. And we only got one constraint, so we only require one Lagrange multiplier with the scalar multiplied by f. So this equal to, so the j equal to this half u1 squared divided by 4 plus u2 squared divided by 9 plus lambda. So now the problem is, what is the f? What is the f? Remember, so from here you can know our standard format for the f is f u equal to 0. So it must be in this form. So we know the form will be f, in this case it's f u1, u2 must be equal to 0. So constraint must be in this form. So you need to properly formulate the original constraint into this form. So it's quite easy. So it's just u1 plus u2 minus 1. This will equal to 0. So we know this will become our f u1 u2. So we can put the lambda f, so this u1 plus 2 u2 minus 1. So next we can evaluate the necessary conditions. So the first one, dh d lambda. dh d lambda, the h is a scalar, the lambda is also a scalar, so it's quite straightforward. So we know to evaluate this one, the first one equal to just equal to 0 because it has nothing to do with lambda. Then we just get this f. This becomes u1 plus 2 u2 minus 1 equal to 0. Remember that this is just equal to our constraint function. It's exactly the same as here. It's exactly the same as u1, u2. Remember that exactly the same as here. So next we can compute the dh du. So in this equation, the h is a scalar and the u is a vector. So you can expect that by evaluating this, we will get a column vector. So this is given by dh du1, dh u2. So this can be easily evaluated from here. So the dh du1 is equal to u1, 2u1. So the 2 will cancel from here. So the u1 divided by 4 is u1 divided by 4. So this u2 will just 0 plus lambda. The other components are just 0. So the dh du2 is also quite simple because we got 2 u2, so the 2 are cancelled at here. u2 divided by 9. So this u2 divided by 9. So the first one is 0. So the u1 is 0, so it's plus 2 lambda. Plus 2 lambda. So this is equal to 0. So from here, we got 3 equations. So we got 3 equations. Is u1 plus 2u2 minus 1 equal to 0. The first one. So the second one is u1 divided by 4 plus lambda equal to 0. So the last one is u2 divided by 9 plus 2 lambda equal to 0. So we have three equations and we have three unknowns, the u1, u2, and lambda. So from this you can easily calculate and derive the values. When you calculate this, you will got a u1 star equal to 1 divided by 10, and u2 star equal to 9 divided by 20. Okay, so these are the solutions to the constraint optimization problem with equality constraints. So the solution are quite standard. So you first construct Hamiltonian. So the Hamiltonian will convert the original problem into an unconstrained optimization problem. So for the unconstrained optimization problem, so we know the necessary condition will be the gradient to be equal to 0. So we set the gradient equal to 0. We will get the solutions. So today we will discuss the third category of problem. It's a constraint. Constraint optimization problem with inequality constraint. Inequality constraints. So the problem formulation is quite similar to the problem with equality constraint. So the formulation is also we want to minimize a scalar cost function. So also we define this J to be scalar. So to represent, for example, the distance from the starting point to destination or traveling time, or say energy we use to travel from starting point to destination, and something like that. So it's a scalar, the scalar function of vector in terms of vector, control input. So the control input, all the control input are real. We define the control input in a real space with n dimensional. So you know this U will be defined as a column vector like this. So it's U1, U2 up to UN. So this is the cost function. So far we have not defined the constraints. So we optimize the above function subject to constraints. So the constraint is also represented by a set of functions. So f, u. So the function is defined as a function of the control input, and we may have multiple functions that put a vector representation here. So So the only difference, so far the definition is the same as the equality constraint problem. So the only difference is now we generalize the constraint, and the constraints can be defined by to be smaller or equal to 0. So our F assume we have M real equations. We have M real equations. So remember that here we define the inequality constraint. Remember in our equality constraint, we always define n is greater than m. That's because if we have more m than n, so actually this equation already be able to decide your control input. So for example, you only got 2 control inputs, and if you have another 2 equality equations, so from 2 equations you already be able to decide the 2 control inputs. There's no need to optimize the function. So in order for the problem to be well defined, you need to define the n to be greater than m. But however, in the inequality constraint, we don't need this condition. So we may have more constraints. We may have more constraints than the control inputs. So later we will use an example to show this. But you just remember that in this set of problems, it's not necessary to define n to be greater than m. So we define this problem as the third category of problem, but actually the problem is not new. We already be able to solve the problem. So if we further look into the problem, we know the problem can be divided into 2 scenarios, into 2 cases. So the first case, the first situation is the constraints are not active, are inactive. The constraints are inactive. So what's the meaning of the constraints are inactive? So assume we use a simple example to illustrate the idea. So assume we define JU. So assume we define a JU to be a quadrature function in a 1-dimensional space. So these are the space for U. So for example, we define the JU. So you may think about this JU to be something like so for example, U minus a constant 1, for example 1 squared, something like this. So if we have a function like this, you know if we plot the JU, it will be in this shape. And in this case, so if we define the JU to be U minus 1 squared, we know the U star will be given by 1. So in this example, you can imagine that here is 1, here is 1. So it's the global minimizing point of the cost function. So for the constraints, so we may define the constraints. So for example, we just define a very simple constraint. We just define a constraint on the range of U. So for example, we define a constraint like this. So we define the u must be smaller or equal to a value at here. So for example, here is 10. So the u is smaller or equal than 10. So if we define a function like this, we can easily convert the function into this form. So we can convert this into a u minus 10 is smaller or equal than 0. So we can define this to be a f. So this will be the standard form, exactly like this. But you just remember that this fu is more flexible. It's more powerful and more flexible. So you can define more complicated constraints. But in this illustrative example, I just define a simple constraint on the range of u. So I define this u to be smaller than or equal to 10. So the u will be in this range. So if we define the constraint this way, we know the solution to this problem will be 1. So in this case, we know the solution to this problem will be inside the boundary. So actually, this boundary are not active. We are not using this condition. So in this case, actually it's equivalent. The problem is equivalent to just minimize the cost function. Just minimize this cost function Gu without any constraint. So in this case, the constraints are inactive. In this case, we convert the problem into an unconstrained problem. Unconstrained optimization problem. So the idea is quite straightforward, right? So we define a constraint, a range for the control input. But however, the global minimizing point is within the range, so it's inside the boundary. So the solution is inside the boundary. So we actually don't need the constraint. The constraints are not active. So in this case, in the case 1, if the constraints are not active, the problem can be converted into an unconstrained optimization problem. So we may have another situation. So another situation, the second case, is constraints. Constraints are active. So we just use the same simple example. So assume we also have the cost function like this. We also define the cost function to be a simple causal function. So for example, u minus 1 square. So in this case, we know that the global minimizing point is given by 1. So the u star is equal to 1. But in this case, we define a different constraint. So for example, So here, assume here is minus, so it's for example minus 5. So now we define the control input in this way. So now we define the u is smaller than or equal to minus 5. So if we define the u in this way, we know we can easily convert the constraint into a standard form. So we can define this fu to be is equal to u minus 5. So u plus 5 is greater than or equal to 0. So we have a new constraint like this. So now we are required to minimize the cost function, but subject to this condition. So we cannot approach u equal 1 because the 1 is outside the boundary. So what will be the solutions to this problem? So the solution to this problem will be given at the boundary. So actually this problem can be converted to another problem. So this is equivalent to minimize scalar function ju. So we want to minimize this scalar function ju with u belongs to R1. But now it's subject to this constraint. In this case, we know the optimizing solution must be obtained at the boundary. So it must be obtained at the boundary. So this is equivalent to minimize this function subject to f u equal to 0. So we convert the inequality constraint into a equality constraint. So this problem is a constraint optimization problem with equality constraint. Equality constraints. So in summary from this simple example, is we may have two scenarios for the problem. So the first case is the constraints are inactive. So in this case, the problem will be converted into a standard unconstrained optimization problem. So the problem formulation is we try to minimize a scalar function with the control input of u. So the u is belong to Rn. So the second case is constraints are active. So in this case, the problem can be formulated to be a standard optimization problem with equality constraints. It's subject to the equality constraint. This must be equal to 0. So from here we know the inequality constraint problem can be divided into these two scenarios. And for either scenario, we already know the solutions. But now the problem is we don't know when the constraints are active and when the constraints are inactive. Before we solve the problem, we don't know whether the constraints are active or not. So the solution to this problem is also to construct the Hamiltonian. So the solution to this problem is to construct the Hamiltonian. We construct the Hamiltonian is a H, so it's the same definition as before. So we define this H in terms of U, in terms of lambda. So this equal to J U plus lambda F. So far it's exactly the same. But remember that, so here the FU, they are inequality constraint. So they are not equal to 0, but smaller than or equal to 0. So we put all these constraints into the Hamiltonian function. So next we can check whether the constraints are active or not. So from here we know we totally got M constraints. So the constraints we have Fi, for the Fi U. So this is smaller than or equal to 0. So we define this I to be equal to 1, 2 up to M. So assume we totally have M constraints. M equality constraint defined in this way. So if the S constraint is smaller than 0, So this constraint is smaller than 0. That means the S inequality constraint is inactive. So if the S equality constraint is inactive. So we know in the Hamiltonian, this problem will be converted into a unconstrained problem. So this is equivalent to this part to be 0. So from here, we know this lambda I corresponding to I should be equal to 0. So we know in the Hamiltonian, this Hamiltonian is in the function is h in the function that j plus lambda 1 f1 plus lambda 2 f2 is up to lambda m fm. So it will be in this form if we expand the vector representation. So in this part is the product between the Lagrange multiplier and the constraints. So for each constraint function, we have a corresponding Lagrange multiplier. So assume the S constraint is not active. That means this part will be ignored. So to ignore this part, we can easily have a condition that Lagrange multiplier to be 0. So secondly, if the constraint, the S constraint equal to 0, so that means this constraint this inequality constraint is active. So if this one is active, we know the constraint active is actually converted into a equality constraint. So this equivalent to an equality constraint. Equality constraint. So in the Lagrange multiplier and the Hamiltonian definition, so if the constraint is active, we know the lambda will not be 0. So actually, this lambda should be greater than 0. So later, shortly, I will show you why we have the lambda is greater than 0. But from here, by this formulation, we already be able to decide. Whether the constraints are active or not, and solve the problem. So the solution to this problem with inequality constraint is also first to construct Hamiltonian. But after that, it will be more complicated. We need to decide all these combinations to see which combination is valid. So I will use a simple example to show why we have this condition. So why we have if the constraint is active, the Lagrange multiplier must be greater than 0. So the reason for this one is actually from in the constraint problem. We remember that we define this pH, du must be equal to 0. So we expand the vector form of the pH du. So this actually gives us the delta J plus delta f multiplied by lambda. So we define this way. So in general, these are a vector. So all these are vector. So all these vectors need to be zero. So in a one-dimensional problem, we have this delta J. Also, for any dimension, we have this delta J plus delta F multiplied by lambda equal to 0. So by using this equation, we can show this lambda will be greater than 0. So I just use an example to show the reason for this one. So we just use a simple example to illustrate the idea. So assume we define J U equal to U square. So we know the global solution for this one will be U star equal to 0 and J star equal to 0. So these are the global solution. So now if we define the constraint, so this subject to, if we define this subject to U is smaller or equal to minus 1. So if we plot the problem like this, so we have this U and the U square, you know, is a quadrature function. So here it's just U equal to 0. So the U equal to 0. But now we define the U must be smaller than or equal to minus 1. So here is minus 1. So these are the constraints. So in this case, we know the constraint. So this constraint is active. So now let's check what are the value for lambda. So we know in this case the constraint is active. So let's decide what's the lambda. Lambda is a positive or negative. So to decide this is very simple. So we decide in this equation we know we need to calculate delta J and delta F. So all these are scalar. So it's very simple. So we know the delta J is given by dj du U equal to minus 1. Evaluate at the boundary. So the dj du is given by this U square. So it's by 2U with U equal to minus 1. So this is given by minus 2. So what about df? So the df is delta f is df du, also U equal to minus 1. So what is the constraint of f? We define this U to be smaller than or equal to 1. We can convert this to be U plus 1 smaller than or equal to 0. So we know the f u is defined by u plus 1. Defined by u plus 1. So the df du is given by d is du, the f equal to u plus 1. So this u equal to minus 1. So we know that du plus 1 du is a constant. It's a constant regardless of your u. So this equal to 1. It's just given by du equal to 1. So in this equation, we know the delta J plus delta F multiplied by lambda is equal to 0. In this equation, we already know this condition. We know this condition from the necessary condition. From the necessary condition derived in our last lecture. So we just put the delta J and the delta F into this equation. So we have the delta J equal to minus 2 plus delta F equal to 1 multiplied by 2. So this equal to 0. So this equal to 0, we can decide the lambda. So we can decide the lambda. So the lambda is given by 2. The lambda is given by 2. So this is greater than 0. So this is the first situation. We may also check another condition. So for example, we have another condition. So this is the first scenario. So the second scenario is assume we have this u, and we have used the same cost function, but now we want to use a range for u like this. So we know the global minimizing point for this one will be 0. But now we have this u to be greater than or equal to 1. So this is the first scenario. So the second scenario, assume we also do this u equal to u square, but we subject to this u is greater than or equal to 1. So to see what happens in this case. So we have this u is greater than or equal to 1. So to convert the constraint into the standard form is given by 1 minus u is smaller than or equal to 0. So we just need to shift the u to the right side. So because we want the standard, remember that we have the standard format of fu is smaller than 0. Remember, we require the standard format. So to construct the standard format, so we just shift this u to the right hand side. So it's 1 minus u is smaller than or equal to 0. So we may define this fu equal to 1 minus u. So in this case, we can calculate delta J equal to dj du, u equal to, now we have the boundary of u equal to 1. So we know the boundary is active, the constraint is active, so u equal to 1. So this equal to dj du, so it's 2u, u equal to 1. So this equal to 2. So we can calculate the f. So the df equal to f equal to df du u equal to 1. So this is given by du. So we have the function of 1 minus u. So u equal to 1. So we know this equal to minus 1. So from the necessary condition, we can determine the Lagrange multiplier. So the delta J plus delta F multiplied by lambda equal to, so the delta J equal to 2 plus delta F equal to minus 1 multiplied by lambda. So this equal to 0. So from this, we can derive the lambda, we can determine the lambda equal to 2. So it's greater than 0. Greater than 0. So now we use this simple one-dimensional example to illustrate or to prove the idea that if your constraint is active, then the lambda must be greater than 0. So far, you just need to remember, you just need to memorize the conclusion here. So later we will use an example to show how to use. So to solve this kind of problem with inequality constraint, so you also need to construct the Hamiltonian. And from the Hamiltonian, we have these two scenarios. If the constraint is not active, then the Lagrange multiplier will be 0. If the constraint is active, then the Lagrange multiplier must be greater than 0. So we have these two scenarios. Okay, so that's all for today.